Aloha kako. Hello, everyone. Welcome to Live from NOIRLab at Gemini. My name is Alyssa Leilani Grace, and I am an outreach assistant at the International Gemini Observatory in Hilo, Hawaii. Before I introduce our guest scientists, please remember that if you have any questions or comments, you can type them into the YouTube chat box, and our moderator, Jamika Marshall, will read them out loud throughout the presentation. Joining me today is Dr. Jason Chu, a science fellow also from the International Gemini Observatory in Hilo, Hawaii. From an early age, Jason developed an interest in science, particularly physics. He attended the University of California at Berkeley, where he received his bachelor's degree in both physics and astrophysics. Upon graduating, he moved to Hawaii for his PhD work at the University of Hawaii's Institute for Astronomy, where he completed his dissertation on the evolution of luminous infrared galaxies across cosmic history. During his time in Hawaii, Jason has been fortunate in having the opportunity to observe on many of the telescopes on Mauna Kea, sparking his interest in photography. There are many similarities between astronomy and photography. Both rely on the recording of light using electronic detectors. Jason especially enjoys taking nighttime and/or long exposure photographs, not only to reveal phenomena imperceptible to the human eye, but also to convey the truly magical views from the summit of Mauna Kea. His photography has appeared in several different US and international astronomy documentaries in recent years. Now, before we let Jason wow us with his photos, let's talk a little bit about Gemini. The International Gemini Observatory is a program of NSF's NOIRLab. Gemini consists of twin telescopes, one on Mauna Kea, Hawaii, and the other on Cerro Pachon, Chile. Gemini is funded by the National Science Foundation and 5 partner countries: Argentina, Brazil, Canada, Chile, and South Korea. All of these countries are allotted time for observations based on their contributions. If we take a look at the telescope itself, we can see that Gemini has a primary mirror with a diameter of 8.1 meters. The open structure of silver beams holding the smaller secondary mirror allows cool night air to pass freely between the two mirrors. Combined with the open sides of the dome, this design ensures a uniform temperature matching the outside environment. On the underside of the telescope is a whole suite of instruments that allow the telescope to collect data in infrared and optical wavelengths. Observations then sometimes produce fantastic images like these. From mini-moons to planets to galaxies and beyond, Gemini and NOIRLab are dedicated to discovering our universe together. And in our most recent Gemini news, we are happy to announce that the Gemini North telescope on Mauna Kea, Hawaii, went back on sky on May 19th. After developing and reviewing appropriate safety protocols in regards to COVID-19, a minimal on-site crew have resumed operations. Majority of the staff in Hilo, Hawaii, myself included, will continue to work from home. And now for Jason's amazing presentation.
Hello, everyone. Well, thank you for the very nice introduction. So just like Alyssa said, a lot of us are right now working from home. So trying to get through this pandemic together. So I just want to thank everyone for all of their efforts in running this observatory, and of course myself included. So now let's get started. So I want to talk about looking up at the Hawaiian skies. So I want to kind of start off with this image because it kind of gives a really nice overview of astronomy in Hawaii. So this is a shot that I took from Mauna Loa, in fact, this past January. And it had just snowed. And so one of the shots that I've always wanted to get was a very nice overview photo of Mauna Kea with its snow. And so what I think this image really shows is how the it shows several different characteristics on what makes Mauna Kea special as far as astronomical observing site. And so one of the things you'll notice with Mauna Kea is that it's a very smooth, kind of like a bump that's rising out of the ocean. And so in this picture, actually, you can't really see the ocean because that's behind some clouds. The clouds are coming in and covering it. But this nice and smooth shape of it allows the air to slowly, or not slowly, but just smoothly flow over the top of the summit. And so that allows for astronomers to be able to look at stars in a clear way. So you might notice that when you're looking at a star at night, that pretty much every star twinkles. But this is bad for astronomers because we're trying to get, our best resolution possible. And so if we have a smoothly flowing airflow going over the top of the mountain, then we get a really nice airflow. And that allows us to get amazing imaging and spectroscopy as well of stars and planets and galaxies and everything. So this was taken at sunset, and this was very, very specifically timed when I took the shot. And so the interesting thing about this photo is that this is one of my first gigapixel images. So this image by itself is actually 1 billion pixels. Obviously, this is downsized for this presentation, but in the original full resolution photo, I can easily resolve and see all the individual telescopes on the top of the mountain, which you can't really see here, but I'll show later. So one of the things I also wanted to kind of show, like Alyssa mentioned earlier, are the different kinds of views that are not as perceptible to the human eye. And so this is from the same location now about an hour and a half or so after sunset. And so there are a lot of things going on here. So we still see the snow up on the mountains, amazingly, even though it was pitch dark, pitch black to me. And we can also see Saddle Road, which connects Hilo to the eastern part of the island. And, western. And so that's what all the lights you see are down here going near the base of the mountain. Now you'll notice that the sky isn't exactly completely dark. And so this is a phenomenon known as air glow. And so air glow happens because there are ions and other molecules and atoms high in our atmosphere that are still kind of excited from the solar radiation from our sun from previously that day. And so these atoms and particles are still excited, and so they give off light. And so we perceive this as air glow. And so that's why you see this interesting menagerie of colors in the night sky right now. So you'll also notice that you can see the Mauna Kea access road, you can see cars coming down. And so I remember when I drove down later that night, there were still lots of cars coming. And so a lot of people in Hawaii, because we live in a tropical climate, they like to go up to the summit and, play in the snow. And some people even bring the snow back down in their trucks and, build snowmen on the beaches here. So that's one very interesting thing that we Hawaii people like to do. So when I was putting this presentation together just a few days ago, I noticed that there were these two little objects at the very top of my image, and I didn't know what they were. So I looked at my original full resolution image, and I was amazed to find that I actually captured two galaxies just within my field of view. And so these two galaxies are called M81, that's the one on the right, and M82, which is the one on the left. And so M82 is actually a well-known starburst galaxy. I personally don't study it, but it's a archetypical example of what a starburst galaxy is. And so amazingly, I was able to resolve this with my camera. Certainly is not something I even noticed with my naked eye when I was taking this photo. So one of the things I also want to cover is why Mauna Kea astronomy is, why Mauna Kea is especially suited for astronomy. And so one of the phenomena that occurs around the mountain is something called an inversion layer. And so what this inversion layer does is it forces and it keeps most of the clouds, most of the tropical clouds below the summit level. And so this photo was taken from about 9,000 feet. So I'm not even near the summit at this point. And so at 9,000 feet behind me is Halepohaku. Halepohaku is where I would go, and all the astronomers, as well as our day crew, would go in the daytime to either eat or sleep. And so at nighttime, right before one of my observing runs, I was able to climb up to this little pu'u or cinder cone, and I captured this photo showing the Milky Way right along the horizon and just about to rise on the left side. So on the left side is looking towards the east, and on the right side is looking towards the west. And you will also see that Mauna Loa is off in a distance, also above the inversion layer of clouds. And so the inversion layer keeps the clouds below the summit level, and that allows the summit of Mauna Kea to observe roughly 300 nights out of 365 per year. So that gives us a lot of time in which we can get science data and discover the wonders of our universe. So one other thing I also want to point out in this photo is you'll notice that there's kind of a diffuse arc that's kind of rising out of the right side and going into the left. So that's a phenomenon called the zodiacal light. And so the zodiacal light is actually caused by dust particles in our solar system that reflects some of that sunlight back towards Earth. And so this was taken right after sunset. So the zodiacal light tends to be the strongest right after sunset and right before sunrise. And so you can even see it curving over to the east. So that actually, I think, has a different name, but it's basically the same thing. If you look closely on the horizon on the right side, you'll see a little bit of an orange glow, and that's actually Kona. And I was able to pick up the light from the city lights from Kona at that point. Similarly, on the on the left side, you'll also see a little bit darker, the lights of Hilo, and that's where actually I am right now. So, yeah. So one of a third reason why Mauna Kea is such a great place for astronomy is that we're actually very far from pretty much any urban population center. The nearest urban population center for us is Honolulu, obviously. This panorama was taken from Diamond Head back in 2014. And I remember this is a very difficult shot to take because I had to hike up there at night. And so this panorama kind of shows, all of the different city lights from Honolulu that if Mauna Kea was near it, would be very bad for astronomy. And that's just because the glow from the city lights can actually be visible in the night sky. So in this photograph, which was obviously from Mauna Kea, you can actually see the the glow of the city lights from Honolulu over about 200 miles away. So even 200 miles away, I can, and over the horizon, I can still see the glow of the lights from Honolulu. And so this photograph also shows another interesting phenomenon that we get on Mauna Kea, and most tall mountains too. So you'll see that there's a triangular shadow on the towards the left side. And so that's actually the shadow of Mauna Kea. And this was taken right as the moon was rising. So you'll notice that it kind of almost looks like sunrise or sunset. But because my camera is so sensitive to low light that I can actually see, I can actually make the sky look like it's daytime. So a lot of times I have people ask me, are these photos taken, how do you see stars in the daytime? And the answer is you actually can't. It's just the moon is out and it makes the sky look so much brighter. So you'll also notice in this photograph, so the two telescopes in the center there are the WM Keck Observatory. So I'll talk a little bit more about the orange lasers that are coming out of it a little bit later, but those are really cool things. And then, so to the left of that is Subaru, which is operated by National Astronomical Observatories of Japan. And on the right side is the NASA Infrared Telescope Facility, and that is being managed by University of Hawaii. And you'll also notice that on the bottom left corner is another telescope called the James Clerk Maxwell Telescope. And so that is a sub-millimeter telescope, and that telescope does not actually look in the optical wavelengths or wavelengths that our eyes are sensitive to. Instead, it's looking at radio wavelengths, actually with wavelengths similar to the microwave oven that you have in your house. So I like to also show an overview of Mauna Kea in observatories overall, just to show where all the telescopes are. This is obviously a daytime shot, so no stars are visible. This was taken about maybe 2 hours before sunset. And so there are a total of 13 different telescopes on the mountain. You can see most of them here. There's one that's not actually visible. It's further down the mountain. So starting on the upper left, we have Subaru telescope, and that's an 8-meter telescope. And then just to the right of that is the twin Keck telescopes. So each Keck telescope is 10 meters in diameter. Then next is the infrared telescope facility. That has about a 3-meter diameter mirror, and that telescope is sensitive only in the infrared. Continuing further to the right is CFHT, or Canada, France, Hawaii telescope, and they also have a 3-meter telescope mirror. Then we have Gemini, which is the telescope that I work at, and so Gemini, we have, like Alyssa said earlier, is an 8-meter telescope, and so we actually have one of the larger diameter telescopes on the mountain. Continuing on to the right is the UH 88-inch telescope, or 2.2-meter telescope. So that was the first telescope that was built on Mauna Kea that is still standing today, and is still being used every night to observe targets like nearby galaxies and other asteroids and things within our solar system. Following that is the United Kingdom Infrared Telescope. Now, UKIRT actually is not under the control by the UK anymore. It's actually under controlled by UH, and is one of the most scientifically productive telescopes on the mountain, if you look at it by number of publications out of it. So currently, a lot of its time is being used to survey the night sky in infrared. So that's also a very useful telescope. Now on the bottom there, we refer to the area sometimes as sub-millimeter valley. And these are some of the radio telescopes that are on the mountain. So starting again on the right side is the sub-millimeter array. And so that is an interferometer. And so what an interferometer does is it uses multiple telescopes that together behave as if it's one telescope. So that way it's easier to control and also easier to build and a lot cheaper as well. In the middle there is, again, the James Clerk Maxwell telescope, and that is a 10-meter, or I think it was 10 or 15 meter, I can't remember the exact diameter now, radio telescope. So that is one of the larger radio telescopes on the mountain. And finally, there is the Caltech Submillimeter Observatory, CSO, on the bottom right. And so that telescope is actually decommissioned and will be removed very soon, within the next few years. So that's a 10.4 meter radio telescope, and there are plans possibly still being worked out. It may or may not be relocated to a different location, not in Hawaii, most likely. So,
all right. Jason and Alyssa, we have some fantastic comments from our YouTube Live audience and a few questions as well.
Great, yeah.
So our first comment is from Liz Fleming, who says she's learning a lot from these presentations. Thank you so much. Also, we have from Saiko Hayashi that your photo is just incredible, the one with the shadow by the moon. She says, oh, wow.
Thank you.
And our first question is from Liz Fleming. She says, how does weather affect your photography? And she has a follow-up question, which is, how does your equipment help you get the best image for specific types of weather?
Yeah, no, those are really, really good questions. So the first question, how does weather affect my photography? A lot. So a lot of these photos were taken when I was still living on Oahu as a graduate student. And so weather was always something that was, so I'm a planner, and so I always look at the schedule, and so I know roughly what's going to happen. and I know what kind of shot I want, and so I know generally what settings to dial in. But yes, weather is pretty much the only variable that I have to really deal with. And actually that, as well as, hoping that the telescope won't break essentially during, their observations. And if they break, then they'll close, and then it's not as interesting. So, there's nothing I can do about that. But as far as weather, so very interestingly, we actually have something called a Mauna Kea Weather Center, which is a dedicated service, not affiliated with the National Weather Service or NOAO, but it's its own service. And what they do is every day, every weekday, they publish a morning and afternoon forecast on what the conditions will be that night on the summit. And so these scientists, actually, these weather scientists, actually run detailed models throughout the day to try and predict certain observing conditions, such as how much clouds there are going to be, how much, what the seeing will be. The seeing is just how much the star is twinkling, basically. And, other things like if they're predicting there to be high humidity. So if we have high humidity, usually above about 75%, most telescopes close because we don't want condensation to happen on the telescope. That will damage the telescope. So I use the Mauna Kea Weather Center as a really good proxy for what I would expect that night as far as weather, and I plan out my my own observing, so to speak, with my photography gear that way. Now, as far as my gear, they're for the most part weather sealed enough that I don't have to worry about. Well, I mean, it's not going to be dunked in a pool or something like that, but condensation. I've definitely had condensation happen a couple of times, but I just kind of dry things out, and it's fine in the end, fortunately. But there are definitely times where I've set up my camera in like 60-mile-per-hour winds. That was pretty scary, not only because for my own sake, but also because my camera can blow over with a tripod, basically. So all these shots I have to put on a tripod so they can take long, up to 30-second exposures. And so I've definitely had a few times where it's blown over, and yeah, my camera was damaged, and I had to send it in to get it fixed. So hopefully that answers your question.
It does. Thank you very much, Jason. I will come back in a few minutes with a few more questions that I see are already being input into the chat.
Great. Yeah, I love questions. So please feel free to, if you have any questions, let me know. So back to this image. So I just want to remind everybody. So this is the image of the entire summit taken from a cinder cone called Pu'upoliahu. And this photo is again taken from the exact same location, and so, but just during a different time of the night. And so I just wanted to show that there's a huge difference between day and night, obviously. And so there's a lot of phenomena and things that we can't really see with our eyes that I can use my camera to reveal. So in this shot, I show all 4 telescopes that have these lasers on them. I'm using them and shining them in the sky. And so this might remind you of a maybe like a rave or like a laser party or I guess laser show. And so we don't do this just for kicks, obviously. These are very expensive laser systems. And so what we do with them is we use it to correct the blur that we see by looking through our atmosphere. So when we're looking at the stars are twinkling, and they twinkle because the atmosphere is moving around and moving that light and diffracting and refracting the light. So it appears to us as twinkling. A really good analogy is if you're looking at the bottom of a clear stream. So as the stream is moving along, it's really hard to see the rocks underneath because the water surface is moving. So what if what we did was we shine a laser at the bottom of the stream, and then we say, well, we know that that's supposed to look like a star. It's supposed to be a point source, a point in the sky. And so obviously it doesn't appear like a point to us because the moving water is distorting the image. And so then what we can do is, and we can take a mirror and we can deform it up to 1,000 times a second. in order to cancel out and correct for that blur. And so what these lasers do is they shine a light to create an artificial star, or what we call a laser guide star, or LGS, in the night sky. This star is created far above the atmosphere. And so the telescope on the ground looks at it and it corrects the mirror. It deforms the mirror up to 1,000 times per second to correct the image and to create a sharper, much sharper image. And so these images, this is called adaptive optics. So these AO type images can actually rival that of Hubble Space Telescope, which is in space and above all of Earth's atmosphere already. So this is technology that was developed originally by the Air Force and declassified in the 90s, and astronomers picked up on it, and we're now using it. And it is very useful in a lot of different breakthroughs in studying, for example, distant quasars and close binary stars and so forth. So one thing I kind of want to step back a little bit and kind of show that Hawaii itself is a very dynamic environment. So as most of you probably know, we have an active volcano on this island. But fortunately, most of the people who live on this island live in a location that's safe. So there's usually only Kilauea that's actually erupting. And so this is from 2014. This is actually a dated photo because you can't actually get this view anymore. So in 2018, there were a series of eruptions near Kilauea, from Kilauea, but just downslope from it, that actually, unfortunately, destroyed about 700 homes. And so that eruption actually stopped the lava flow going to the summit of Kilauea. So this is actually taken from the summit of Kilauea, and you can see the Milky Way behind it, right behind all those, all the gas that's being lit up. So, yep.
I have a quick question for you, Jason, about that previous photo. The small glow in the background of the photo towards the left, is that Pu'o'o?
I don't actually think so. It definitely could be, but I think it's actually one of the smaller communities. I don't remember what the name of it is, but the community that's closest to Kilauea. So, but I don't think it's Pu'o'o. But I'll have to actually look into that. I'll have to look on Google Earth to try and figure out what that is actually. So, thanks.
We also have a question from our YouTube Live audience.
Go ahead. Yes.
All right. So this question is from Jocelyn Ferreira. And she says, what's the shortest exposure time you use for photographing the lasers, Jason?
Oh, very good question. So, well, okay, I mean, it depends on several different factors, but as a kind of a zeroth order answer to your question, I know a GoPro can actually capture it because one of our staff SOSs, or science operations specialist, Christy, I believe, actually has GoPro footage of lasers, I think when she was at Gemini South. But to answer more precisely, it also depends a little bit on your ISO, which is your sensitivity of your camera sensor, as well as the aperture of the camera. But if you're using like point and shoot cameras, you can probably see the lasers with about a 1 to 2 second, I would guess, exposure. So roughly speaking, yeah, and tripod. So I recommend a tripod.
Thank you, Jason. And a quick follow-up, you mentioned something about aperture. What is aperture?
Sorry, yes. So aperture is, so when you're taking a photo, the aperture is the size of the opening of the lens, basically. So the lens has a certain diameter, but then there's a little iris, a little thing that can actually change the how much light is passing through the camera. So a larger aperture will allow more light through and thus a brighter image. So.
Excellent. Thank you, Jason. I'll be back in a few moments with more comments and questions.
Great, thanks. So this photograph here also shows, this was taken in August of 2018. So when the eruptions have been going on for a couple of months by this point. So this is looking towards actually the second major flow, what we call the fissure 8 flow. And so the light from the lava flow, which was a couple miles long, actually lights up all the clouds. And I was fortunate enough to capture the Milky Way above it. So unfortunately, the time lapse from that shot was not the greatest because of all the clouds, and I wanted to go back, within a week to capture it again. Unfortunately for me, but fortunately for the people living in Puna at the time, the flows actually stopped. So this is the best photo I have from that view. So, okay, so kind of going back, so a lot of people don't realize that, we in Hawaii actually get snow, and we do. So this photograph, if anything, proves that. This is not the most amount of snow we've gotten, but this is probably a nice clear view of it. So this was shot from Mauna Loa, and right before the sun had set. So you can still see the sunlight reflecting off the snow. And so as I mentioned earlier, if you zoom in on the photo, you can actually see the individual telescopes, and indeed you can. So you can see, for example, Subaru is there visible on the very left side, followed by Keck, both twin Keck telescopes to its left, right, and followed by RTF, as well as Gemini. If you look closely enough, Gemini is the tallest cylinderish looking object on the very right side. So yeah. So one of the other major characteristics that makes Hawaii such a special place for astronomy is the fact that our latitude is about 19 degrees north. And so that places us very, very close to the equator. And what that means as far as observing the night sky goes is we can actually see the majority of the southern hemisphere, the southern sky, as well as all of the northern sky. So in this photograph, we're actually looking towards the south. The Milky Way is rising in the east. So east is, in this case, on the left, and Mauna Loa is off in the distance. And so if I go to the next slide, you can actually see these are most of these are southern constellations. Most of us are not really familiar with them because we don't live in the southern hemisphere, and thus we don't see most of them. But from Hawaii, we can see quite a majority of them. So I also want to point out that the constellation of Crux, or the Southern Cross, is actually visible just above the left slopes of Mauna Loa. And so Crux is a major recognizable constellation in the Southern Hemisphere. And I've also added in several other more nearby terrestrial locations that we're familiar with. For example, Kailua Kona is on the very, very right side. Hilo is on the left side, and Halepohaku, which is where astronomers stay during the daytime, is right in the foreground. And also, incidentally, at this point, we can also see Kilauea Crater, the glow from Kilauea Crater kind of permeating through the clouds just to the left of center.
Jason, this is such a great photo that I'd really like to talk a little bit about one of the constellations, the Southern Cross.
Sure.
So a fun fact is that for the Polynesian navigational star lines, the Southern Cross is really important for identifying the latitude of Hawaii. And so if you look at the Southern Cross constellation there, the two vertical stars that make up the top and bottom of the cross, the distance between those two are actually equal to the distance between the bottom star and our horizon here in Hawaii. It's a little hard to see in this picture because we have Mauna Loa, of course, blocking that horizon view, but it's just a really fun fact, and I love teaching that to kids in our area.
Yes, definitely. Yeah, thank you for adding that. So yeah, right. And like Alyssa said, actually, what the Polynesian navigators do is that when Crux is upright, so maybe about an hour before this photo was taken, when it was more upright, that actually the top and bottom stars of the cross actually points to within a few degrees of directly due south. And so when Polynesian navigators go south of the equator, they can't actually use Polaris or the North Star to determine their latitude and thus location. So they have to resort to using Crux in the south to determine their location. So thank you. Yeah. And so, of course, maybe some of us are aware of some more recognizable constellations, such as Scorpius, which is right near the center of the Milky Way, as well as Sagittarius. So both of them straddle the center of the Milky Way. So this is a very, very nice evening sunset panorama that I shot of Gemini North. So at this point, this was in 2014. So Gemini, we had not transitioned to operations from our base facility in Hilo. So before 2015, observers and telescope operators would have to go to the summit to observe. So you can actually see their car, their SUV right in the bottom right there. And so you'll notice that the vent gates for Gemini are open. And so this allows the evening air to flow in and to equalize the temperature inside the telescope dome and outside. And so this helps eliminate a certain phenomenon called dome steaming. So when we have uneven distributions of temperature between inside and outside of the telescope, that can induce certain blurring of imaging when we're looking through the telescope. So in order to combat that, when Gemini was designed, they put in vent gates on the sides, which allows the air to go through and easily mix and make the distribution of temperature even between inside and outside. So again, on just to the right side, you can actually see the shadow of Mauna Kea again as a triangle. So the sun is setting directly behind that shadow, since we're on the summit of near the summit of Mauna Kea, and the sun is right behind us. Now, the true summit is actually on the very, very right side. You can see that the sunlight is still hitting on just to the top, just the very, very top. And so that area holds a very special significance to Native Hawaiians. And so that area has always been respected and never been disturbed.
Thank you so much, Jason. We
Yes.
have a few comments and a question from our YouTube Live audience.
Great.
First comment is a follow-up from Jocelyn. She says, thank you, Jason. And she remembers Christy's video that you were referring to.
Okay.
And our question comes from Liz Fleming, and she says, what equipment does a novice photographer need to begin taking great pictures of the night sky?
Yes, that's a very awesome question. So, the way I want to answer is basically how I got into it. So I started with a pretty basic digital SLR camera. So, you know, if you can go out and I personally use Nikon brand, but any camera brand will work as long as you can control the shutter speed, aperture, and ISO, which is the ISO is the sensor's sensitivity to light. If you can do it all in manual and also manually focus the camera on your own, then that would be a great way to start. So just as a quick primer, you also need a tripod to go with that. And so one of the key things you have to do is you have to focus the camera manually. So what you can do is you can focus on something at infinity, you know, before the sun goes down. Then you lock the focus. You just turn off the autofocus for your lens, and then you just basically take some very long exposures. So you put it on a tripod and just press the button, and you know, just experiment around. So that's one thing I think that I really want to emphasize is, you know, to even get into it, just have fun. You know, you don't need anything super expensive. You know, DSLR that's probably like a couple $100 is sufficient, is more than enough. And I was able to get great shots even, you know, with my, you know, basic DSLR, you know, I don't know what now, almost 10 years ago now. So yeah, hopefully that answers your question.
It definitely does, Jason. But I do have another follow-up question. You mentioned a DSLR camera. Can you tell us what that acronym stands for?
Okay, yeah. So so we'll start with SLR. So SLR stands for single lens reflex camera, and what that means is you have a camera with a sensor, and it has a mirror. And so what that mirror allows you to do is allows you to see exactly what the camera will see when the picture is being taken. So it's a single lens, one lens, and the reflexes just means that there's a mirror that will flip out of view when you take the photo. And then the digital part is pretty obvious. It's a digital sensor in the back, not film. So back in the old film days, we call them SLRs. These days we call them DSLRs. I actually, believe it or not, I still actually shoot film. There are several types of shots that aren't really possible with digital. Surprise, surprise. So one of them is actually taking ultra long exposures of like up to 5, 6, 8 hours. And so I just set the camera down and compose in the dark, and hopefully I get it right. And I basically press the shutter and I come back like 5 hours later. So I've got some really, really cool shots with that too. And so as the sky is moving, it'll create star trails, and I'll show a couple star trail images in coming up. So.
Excellent. Thank you, Jason. I'll be back in a few minutes with a few more comments and another question.
Great, thank you. Okay, so let's move on. So yeah, very good timing. So this is a photograph now. So there are a couple different ways of doing star trail images. One of them is how I've already mentioned. You can just put down a film camera and just let it run for 5 hours. But another way is to take 30-second exposures repeatedly, and then afterwards on my computer I can so-called stack them together, or basically just kind of add them up together. And so then what we'll see is the sky moving around, and so at the center of all those concentric circles is the exact center is what we call the North Celestial Pole. And so that is the point in the sky that is directly above the North Pole of Earth. So if you're standing at the North Pole of Earth, and if you're going to look exactly or directly above you, then that will be the point. We call that the North Celestial Pole. Polaris, or the North Star, actually isn't at exactly the center or the North Celestial Pole. It's actually about 1.5 degrees or so away. So you can actually see Polaris as that bright star kind of around the 7 o'clock position of this image. Now, as far as the telescopes go, you'll notice that these laser beams will track across the sky, because they're tracking a specific target on the sky, and if the sky is moving, the laser beam is going to be moving. And so these laser beams appear curved because this shot was actually taken with a fisheye lens. So it purposely distorts the image, but it also gives a much wider view of the shot. So that's why the laser light is bending, even though light should not be bending that much. And you can also see several different other things. You can see, so back then, when we use the laser, one of the things we always want to avoid, for obvious reasons, is to avoid shining the laser into a pilot's eyes, someone who's flying a plane. So back then, we actually had plane spotters up there. You can see his flashlight off just to the very, very right side of the image there. But nowadays, because we have other ways of mitigating that sort of risk, we don't actually need laser spotters anymore. So there's a sensor at the top of the telescope that is sensitive to, it's called TBAD. It's basically sensitive to an emergency frequency broadcaster, I believe, that's on every plane. So if there's any plane that gets within, I think, like 10 or 15 degrees usually of the laser beam, then it'll automatically shutter the laser or turn off the laser, so that there's no risk there. Also, interesting fact is that every night we have laser operations, we have to get clearance from Space Command. We send them our targets, and so they come back and say, okay, these are the times you're allowed to propagate the laser, and these are the times you're not allowed to propagate the laser. And the last thing I want to mention is the Keck laser is pretty obvious, as well as Gemini's. But if you look very closely, I'm not sure if this will show up on a YouTube video, but Subaru on the very, very on the right side, the left side, just to the left of Keck, in fact, you can see a very, very faint laser beam coming out of their telescope as well. So, and finally, you'll also see the streaks of light from either me or somebody else driving around the summit at night. So, actually, one thing to note there is that when we're driving around at night, we try and keep our lights to a minimum possible, because it can definitely affect scientific data. So if anybody does go up there, we highly encourage them to turn on the lowest lights possible if driving around. So, but while being safe. So it's important to be safe, but also to try not ruin other people's science. So some of these people, some scientists, spend years preparing and proposing for their data, and so to have it ruined last minute really sucks for them. So.
Thank you so much, Jason. All right, we are back to our YouTube Live audience for a few questions. Our first question is from Michael Mosby. Michael Mosby asks, how often do we get snow at the observatory?
Yeah, that's a very good question. So historically, what I've heard is pretty much every winter we get snow. In fact, well, that still happens, but I know back in the 70s, it tends to happen a lot more often than it does nowadays. So nowadays, I would say probably anywhere from like, 1 or 2 to maybe 5 times a year. Normally, it's like earliest I would say is late November through probably March, I would say is pretty much when you'll get snow as a broad range. So yeah. And of course, the amount of snowfall also, will vary. Sometimes it'll be, just a dusting where it won't even be anything, after a few hours, it'll just melt. Other times we'll get basically full on blizzard style. And basically then we have snow plows that actually go up and have to clear the road. And when that happens, it can be as deep as like, I think 3 feet of snow, 4 feet, maybe even certain places. Yeah. So snow is it actually can be a problem sometimes. We've definitely lost observing nights because of snow and humidity and rain and hail, and and even when Kilauea was erupting, we even had to be careful of the ash from that was coming out of the volcano. Ash clouds can go up to more than 30,000 feet. Mauna Kea is only at about just under 14,000 feet, so it can definitely put the telescope at risk. So hopefully that answers your question, plus some more.
Absolutely, Jason, thank you. Our next question is from Jocelyn, who asks, what's one of the most frustrating mistakes or time-wasting events that has happened to you during astrophotography?
Oh yeah, so my wife would know a lot about that because there are definitely times I get frustrated, but not often, fortunately, as I'm sure she would tell you. She's actually watching right now, probably about a minute behind. But but I would say the most frustrating is sometimes, and just to show that we're all human. Sometimes I will still just forget the most basic things, like I'll just forget to turn off my autofocus, and my camera will try and autofocus at night, and it will not focus, or it will not take a photo. And so what I forgot to kind of mention was that a lot of my work I do are time lapses, and so I'm basically taking a photo from the same exact location and same exact pointing over and over. As the sky changes and as telescopes move and observe. And so if it can't take a picture, then I won't get a time lapse out of it. But fortunately, that hasn't happened for a critical shot. So, but I will say that besides that, one of my most absolute stressful moments was, so I had scheduled with Keck Observatory. It took me just under a year to schedule just a one-night shoot from inside the dome at night while the lasers are being used. And so actually I'll show some of those photographs in just a moment. And so I was going to fly over from Oahu, and I was going to go up the summit that afternoon, set up the cameras by 4 p.m., and then we have to be out of there, and my cameras would start automatically. And it turns out that the taxi I scheduled in Honolulu forgot about me, so I had to drive to the airport, and then I thought for sure I was going to miss my flight, but then somehow my flight was delayed by half an hour. I made my flight, and then driving up there, I was basically assembling and putting my tripods together because when I'm traveling I have to take things apart. And so in the van, my friend was driving and I'm in the back putting all my tripods and camera gear together and making sure all the settings were right. And so but I was able to, in the end, still set everything up, and it was difficult. It's very, very stressful, but it's done. It was done. So yeah, that was a fun, interesting experience.
Glad it turned out all right.
Yeah. Oh yeah, especially after taking a year and working through in the Hawaii Film Office and going through Mauna Kea, Office of Mauna Kea Management. So there was a lot of other background bureaucratic hoops to jump through as well to even do that in the first place. So anyway, so this photograph shows Gemini, our 8-meter telescope, Gemini North, on the left side, with the Milky Way just kind of arcing across the sky from left to right. And so on the right side, you can see just part of the flank of Mauna Loa off in the distance. Closer in, that's the true summit right there, just to the just to the left of Mauna Loa. Behind the true summit, you can see the faint glow of Kilauea. And in the center of the photograph, just below the clouds, is actually Hilo. So one of the side benefits or byproducts of the fact that we have lots of clouds in Hilo, besides keeping us cooler on warmer days like today, is that actually also blocks out most of the light from Hilo. So that's also really, really beneficial to us. So, kind of going back to the question about weather, we definitely get lots of inclement weather on Mauna Kea, but in this case, this photograph actually shows a lightning strike on Mauna Loa, as seen from Halepohaku, which is where all the astronomers stay. It's right around sunset. So you can actually see the lightning strike. It was actually a cloud to ground strike there. You can also see just a tiny bit of the Milky Way, just to the upper part of the image, upper right part of the image. And that super bright star, or quote star, is actually Venus. So Venus at that point, at that time, was actually in the evening time. So it was the evening star. So this was a long exposure, I believe, of only about 5 seconds, or 5 or 10 seconds. And so I took these images over and over, hoping that I would capture a lightning strike in one of my long exposures. So that's actually how I captured this image. So, and this is actually part of a time lapse, which, if you've seen some of the NOIRLab commercials, not commercials, but just when NOIRLab was publicizing my talk, they also published some of the time-lapse videos that I've done for the mountain. So any questions?
In fact, we do have a few more questions and a few comments. So let's first go to a question. This question is from Genevieve. Genevieve asks, is a prime or zoom lens better?
Oh, okay, yeah, the age-old question. Okay, clearly she's a photographer, so that's great. So it depends on what you're going for. So and depends a little bit on the camera brand that you're using. So I personally use Nikon, and so for us Nikon users, the 14-24 f2.8 lens is phenomenal. It's starting to show a little bit of its age right now, but it's still really, really sharp, except for the extreme corners. And that is a zoom lens, and it still works great. But other times, there are definitely times when I've used, for example, the Sigma 18-35 f1.8 lens. Again, that's another zoom lens that's a very large aperture that lets a lot of light through. But yes, I do sometimes use prime lenses, or basically lenses with only a single focal length. You can't zoom it. And so for those situations, I've used, for example, the 105 f1.4 lens. So that photograph I showed towards the very, very beginning of the wide view of Mauna Kea with the sky glow, that shot was actually done with that 105 medium telephoto lens. And so what makes that such a difficult shot was that I had to mosaic or put together, I think, around 16 or so individual shots together to merge together to create that full wide view. So it kind of depends on your situation. The last thing I want to mention is that as far as lenses go, one of the most important things for astrophotography, or astro landscape photography, which is pretty much what I'm showing, is to make sure that the lens has really good chroma control. Otherwise, towards the corner and towards the edges of pictures, you'll get these weird blobs that are kind of the shape of comets. And so that's an effect. That's an effect from the optical construction of the lens. And so certain lenses can reduce that better than other lenses. So.
Jason, thanks so much for all of these photos, and thank you everyone for your questions in the chat. Keep them coming. We have 4 more minutes left of our presentation. So for these last 4 minutes, I'd really love to be able to show people where to follow Jason and his amazing photography on social media, and where to also follow NOIRLab and all of our amazing photos, sometimes featuring Jason's photos. So if we could just put up that slide and answer the rest of the questions.
Sure, yeah. So there's actually just probably one or a few more photos I want to show. So I'll skip this one. I'll skip just a few. I'll talk about this one. So this is Gemini. So we were commissioning the laser at this point. And so this laser at this point was pointed stationary in the sky right at the North Star. So because the sky is rotating around Polaris at that, all the time, all the stars appear to be just rotating around the lasers, which is super, super cool. And just the last picture I want to just show is not that one. So this is the inside of Keck. Is actually not that one. This one. So what I like to show about this one is that there are a lot of telescopes on Mauna Kea, and all the telescopes cooperate together. And we all have the same exact mission, and that is to just explore and reveal our universe and together. And so it doesn't matter if we're Keck Observatory or Subaru or Gemini. So Gemini's laser is actually coming off the image on the left side there. But we're all focused on the same thing, and that's discovering our universe together. So thank you, everyone. Sorry for taking a really long time. So I'll take questions now.
Fantastic, Jason. We do have a few more questions and a comment. So our question here is from Liz Fleming, who asks, can she get a pretty decent picture using her camera phone?
Yes, I think the latest cell phones can actually do it. So I think the latest Google Pixel, I don't remember what number it's on right now, 5, I think, actually can take night photographs. I personally haven't tried it because for one, I don't have it. But I remember seeing, these Google's ads for it. And if you find a tripod or something at least that can hold the camera still, I'm pretty sure it has a long exposure mode. And I believe also the latest Samsung phones, the S20, I think, also can do longer exposures of like maybe up to 5 seconds or 10 seconds. So definitely give it a try. Yeah, so the most important thing is to focus it, but to also just do a long exposure with a tripod.
Excellent. Thank you, Jason. And a few more comments to wrap up. Saiko says, thank you, Jason, for sharing this, your great work and your passion. Dale and Harriet Dupuis say they don't have any questions, but they wanted to say hello from Louisiana, from Shreveport.
Cool. Yeah.
And Genevieve also says, thank you so much, Jason. She loves Nikons. Also have Atsuko saying, amazing photos. Every one of them are breathtaking. And last but not least, Liz Fleming says, yes, these are amazing photos. We'd like to thank everyone who joined us in our YouTube live audience today.
Great. Thank you, everyone. Have a good and safe day.
Okay, mahalo for joining us today, Jason, and mahalo to all of our viewers. If you have any more questions or comments, find us on social media at NOIRLab Astro. We'll see you here again next week with Gemma intern Odysseus Quarles and Michael Wong of UC Berkeley discussing NOIRLab's newest Jupiter images, such as the one right behind me. So take care and a hui ho.